says, in a random sample of machine parts, 18 out of 225 were damaged in a shipment. Establish a 95% confidence interval estimate for the proportion of damaged machine parts in the shipment. So the first thing is P that we talked about, and I looked around at some of you. It looked good. P is the proportion, the true proportion is what we're looking for. We're looking for the true proportion of damaged machine parts in a shipment. And we have a sample, so we have a P hat. So you would want to write in that first part that P hat is 18 out of 25, okay? So in part 1, we're looking through this. Let's say that this is the true, or this is the, what is our parameter of interest? It is the proportion. Oh, that was nice. It is the proportion of damaged machine parts in a shipment, right? And we have P hat, which you would make with the sign, and that is 18 out of 225. What is that decimal if you do 18 out of 225? 0.08. Okay, so you do want to write the decimal. So make sure you write the decimal with the fraction, okay? So you do want to have that. A is our assumption, so we have random. It says random sample of machine parts, so you can make a check there. Number 2, independent. We assume there are more than 2,250 machine parts in the shipment, okay? Because we're talking about that one shipment, so we assume there's more than 10 times that many. So we assume that there are more than 2,250 machine parts in the shipment. And then normal. So N times P is greater than or equal to 10. That would be 18 is greater than or equal to 10. So that would be a check. And then N times 1 minus P is greater than or equal to 10. And that would be 207 is greater than or equal to 10. And that would be a check. So it passes our 3 conditions. For N, we just talked about it is a 1 proportion Z interval. For I, we wanted to find the actual interval. So what was the interval? Everybody else get that? Okay. So it comes straight from the calculator. So you got a stat test. Go to 1 proportion Z interval. That should be like letter A on your calculator. And then you will be able to get that interval from your calculator. And then the last part, again, is the most important. But that would be our conclusion. So in our conclusion, we want to say we are, and we look at the thing, we're doing 95%. We are 95% confident that the true proportion of damaged machine parts in the shipment is between 0.04455 and 0.11545. So there's no extra sentence there when you're only doing 1 proportion. When you're doing 2 proportion, remember we're looking at the difference between 2 things. And then we end up, when we're looking at the difference between the 2, we end up seeing if 0 is in the interval or not. Okay. So we would say because 0 is in the interval, this, and because it's not, that. That's when we get to 2 proportion. So PANIC, that takes you through that whole thing. That was kind of a brief little review over 1 proportion since we're done with that and we've moved forward to the 2 proportions. Okay. So the next thing that we're going to look at real quick is this brief, just so you have time to go over it. We're going to look at this brief video. So I've given you the questions on it. So that was the last thing I gave you. So if you look at those questions, and I'll pull up this video. The video is from the Against All Odds series, which is the same thing we've looked at for some of the other topics in statistics. If you look at it, it has pretty much, it goes in the order that we teach it. It goes through all the things at the beginning of the statistics course and takes you all the way through probability and other things, sampling distributions. And now we're down here in these last few. If you see, the last ones are summaries. So we're actually in the last couple here: confidence intervals, test of significance, means, proportions. So we're going to look at just what are confidence intervals and where will you see them outside of the class. And so an example here that they're going to give in this video is a battery manufacturer test a sample of its product. So they're testing so many batteries to verify its claims about battery life. So like if you buy a certain battery, they'll say it lasts so many hours, on average. Where do they get that from? So they're getting it from this. And it says a margin of error and a confidence level will help quantify its accuracy. So it helps tell you how accurate it is or not. So that's what we're going to look at right now before we go to those last two pages. Okay? All right.
Funding for this program is provided by Annenberg Learning.
All the questions will follow through.
Hello, I'm Pardeep Sabeti, and this is Against All Odds, where we make statistics count. You're probably an expert on sampling by now. You know the point isn't to report about the individuals in your sample, but to extrapolate from the information you have about them to something about the whole population. That's the basis of statistical inference, estimating a population parameter from your sample statistic. For a quick refresher, let's use the example of a patient's blood pressure. A nurse takes one blood pressure reading at one moment in time. But of course, blood pressure actually varies throughout the day or the week, depending on things like if you're rushing around, super stressed, or just relaxing on the couch. We'd get a better picture of one person's overall mean blood pressure, the population parameter, if we take a bunch of readings and calculate their mean, the sample statistic. Okay, so let's say twice a day for a week, we measured our patient's systolic blood pressure. That's the force of blood in the arteries as the heart beats. The mean of those readings was 130. But how well does that number, based on our sample, really match the true value of his mean blood pressure? In other words, how trustworthy is our conclusion? After all, we might have come up with a number other than 130 for the mean if the readings that happened to be in our sample were higher or lower. Well, statisticians address this issue by calculating confidence intervals. Rather than a single number, like 130, we can compute a range of values along with a confidence level for that range. The ability to state a precise confidence interval is extremely useful, particularly when millions of dollars are riding on your answer. That's the situation in the highly competitive business of batteries.
The Duracell batteries we make now live longer than the ones from a few years back.
Battery companies have always trumpeted their products' long lives in their commercials. Because the companies promise specific improvements in battery lifetimes, they need proof before the ads go on the air. Back on the factory floor, like here at Kodak's Ultra Technologies, technicians use rigorous testing and construct confidence intervals to back up the marketer's claims.
When we're creating a confidence interval, there are many things we have to take into account. One, we have to see that we have a normal distribution. We have to have representative samples of the product.
Random samples of batteries are pulled from the warehouse. Then it's time for the rack, a device from which no battery emerges alive. The rack is more subdued in appearance than the toys, clocks, and flashlights these AAs might have been headed for, but it's mimicking the load of real products. It might seem more fun to test the batteries in these actual products themselves, but the rack provides a much more controlled environment.
You have the variable of the life of the battery, but also the variable of the performance of the toy.
As the batteries continue to discharge in the standard test, the computer turns them on and off in cycles that represent the consumer's typical use pattern. Battery voltage is constantly monitored, keeping careful track of when each battery runs out of juice.
The computer will compile for you the mean value, the standard deviation of that data, and you can go ahead to the final step of creating the confidence interval with that data. The parameters you need, of course, to calculate that are the mean, the standard deviation, and the sample size, and your choice of what confidence interval you want. And what we can report in our engineering report is that this population of AA batteries, when used in a toy, can be considered to last 7.5 hours plus or minus 20 minutes, and our confidence in that range is 95%. Our management can go ahead and make decisions based on that confidence level.
Let's retrace Kodak's steps and figure out how they came up with this confidence interval. Before we even get started, we need to make a few assumptions. One, that we're working with independent observations. The life of one battery doesn't affect the lives of any of the others. Two, that our data are from a normal population, where the sample size is sufficiently large. That's reasonable. And three, that we know the population standard deviation. That's actually not a reasonable assumption in the real world, and there are ways to get around the problem. But for now, we'll assume we do know the standard deviation sigma. Our sample mean X-bar is what statisticians call a point estimate. It's a single number statistic that can be used to estimate a single number for the population parameter mu. One problem with using the sample mean X-bar to infer the population mean mu is that X-bar can vary depending on the sample we take. If we randomly included a different selection of batteries in our test sample, we would likely have wound up with a different value for X-bar. A single number like X-bar is not a very helpful estimate of mu without some indication of how accurate it is. Including a margin of error allows us to move beyond just a point estimate. Luckily, we know that since the sampling distribution of X-bar is normal, the mean of the sampling distribution, the mu of X-bar, is the same as the unknown mean of the population mu. We also know that the variability of X-bar is described by its standard deviation, which we can calculate with this familiar formula. In this case, the population standard deviation sigma is 63.
Now, this is when we go to one mean. When we talk about means, that's going to be part of the formula, is sigma over the square root of n. When we're doing proportion, it's been the square root of p times 1 minus p over n. But this is the formula for means. They're all on the formula sheet. But we did this in sampling distributions for mean also.
3.5 minutes, and n, the number of batteries in our sample, is 40, so sigma of X-bar is about 10 minutes. Think back to our 68, 95, 99.7 rule. In any normal distribution, 95% of observations lie within plus or minus 2 standard deviations of the mean. So 95% of all possible battery life samples give data so that mu is within plus or minus 20 minutes of that sample's X-bar. The population mean mu is unknown, but we do know that 95% of the population samples we would ever take would have an X-bar that is within plus or minus 20. Here, X-bar was 450 minutes. So we can say with 95% confidence that mu lies within 20 of X-bar. This interval, X-bar plus or minus 20, is called the confidence interval. To say that we are 95% confident in our calculated range means that we got the numbers using a method that gives correct results 95% of the time. In other words, that's how likely it is that the method we use to compute the range actually comes up with an interval that contains the unknown population mean. Think of the interval as a net. Each time we take a new sample, we throw the net again. Sometimes we catch mu, and sometimes we miss it. Here's the interval from one sample. It contains mu. Here's a second, another catch. And a third, well, that one missed. We can never know whether a particular confidence interval, like the one Kodak came up with for battery life, is a hit or a miss. But we do know that as we continue to take samples, we will catch the true value of mu 95% of the time over many, many samples. In other words, the probability that the method works is 0.95. So when we say that we are 95% sure that Kodak's batteries last between 430 and 470 minutes, we mean we got this interval by a method that works 95% of the time. What if Kodak were willing to settle for only 90% confidence? Or what if they insist on 99% confidence? In that case, we need to find the z-value that leaves just 1% of the area under the curve in these tails. Statisticians have a general equation that will allow us to compute any confidence level we'd like. Here's the formula. Using the z-table, or software to figure out the value for any critical values, called z-star, on the normal curve you can create a confidence interval for any confidence level your heart desires. You always wind up with something in the form of a point estimate, plus or minus a margin of error. Though we can never achieve 100% confidence level in statistics, I am completely sure that these concepts will come in handy as we move forward. Stick with us to find out how. For Against All Odds, I'm Pardeep Subedi.
Okay, so that gives you a little idea of the confidence intervals and just kind of how that works as you go through. Okay, so let's look at question number 1. So we can we'll go through that one together, and then question number 2 we'll leave kind of for you to, we'll have you talk through it and see if you can work through. So question number 1, let's go through it together again, and hopefully that'll clear up any misconceptions you might have about two proportions or any other questions you still might have about two proportions before we do the next problem. So an assembly line does a quality check, it says, by sampling 50 of its products. It finds that 16% of the parts are defective. A competitor company does the same quality check on 60 of its products and finds that 12 are defective. So the key here is, at the beginning, is what we're trying to find, and that is the parameter of interest. So we're trying to find the difference in proportions of defective products, right, between the two companies. Okay, so P1 is going to be, we'll make the first one, the P hat, our first sample, be the assembly line, and we'll make the second one be our competitor. And so you have to label which one is P1 and which one is P2. That's very important. Even though it seems obvious that P1 would be the first one you get in the problem, some people will put it differently, so you have to let the person know which one is your first proportion and which one is your second proportion from the problem. So the assembly line, there are 50, so we know there's 50 total, and we know that 16% are defective. So how many out of 50 are defective? Yes, 8. Good. So 8 out of 50. The competitor, it says that 12 out of 60 are defective. So what is that proportion? Yep, 0.20. Because, 12 times 5 would give us 60, so 20% right there. So 20%. So we have our proportions and we have our fractions and everything. So we're good for that first part. Okay? So that's a key. The key is to say exactly what it is we're looking for. We're looking for the difference in the proportion of defective products between the two companies. The first proportion we're looking at is the assembly line. We don't have a name of the company. It just says the assembly line. The second proportion we're looking at is their competitor. Okay? And so those are the two. Now, we look at their assumptions, which takes a little bit longer, right, when we're doing the two proportions. It takes just a little bit longer to go through. But the first one is that it is random, okay? Now, it doesn't say on here that it's random, so we can put in there that it doesn't say that it's random. But, all right, so random, it does a quality check. So both of them have quality checks. But it doesn't say that it's random, but it does say it's a quality check. So we'll check it off there. Number 2 is independent. So we assume more than 500 products from the assembly line, and we assume more than 600 products from their competitor. Remember that it should be 10 times the size of the sample. Remember, it should be 10 times the size of the sample. So the 2 samples were 50 and 60. So we don't know how big their population is, so we just assume that it's big enough, right? We assume that there's more than that many. Then the last one is our normal, and this is actually the first time where it's going to fail the normal condition. So we have N1 and P1 greater than or equal to 10. N1 and 1 minus P1 greater than or equal to 10. N2 and P2 greater than or equal to 10. N2 and 1 minus P2 greater than or equal to 10. So the first fraction, you have 8 is greater than or equal to 10. That is not true, so we get an X. Then you have 42 greater than or equal to 10. That is true. Then you have 12 greater than or equal to 10. That is true. And 60 minus 12 gives you 48 greater than or equal to 10. That is true. So it did not pass the normal condition. That means we basically don't have a big enough sample size because there's only 8 that are defective. So it would be, what would help for it to pass the normal condition is to get a bigger sample. And you can always say that in your conclusion. If it doesn't pass the normal condition, you can say taking a larger sample may benefit that. So then we go to N. I can put that down at the bottom. Obviously, this is a 2 proportioned Z interval. Now, just so we know, and so we've seen this before, I'm going to give you for the problem, let's look at what the actual interval would look like, okay? So all we've done is put in the calculator for 2 proportion. We haven't actually looked at what the interval would look like, so let's look at what it would look like. So it would be, so it is P1 minus P2. That would be your statistic, like your estimate. You would subtract the 2. Plus or minus the Z-score, and then we have that big square root. We have P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. That comes from your formula sheet. If you remember, that is the that's on the formula sheet, but that's the standard error is what they call it. So if we plugged all that stuff in, like I'm going to just to kind of go through it. So P1 minus P2, that would be for the interval. That would be 0.16 minus 0.20, plus or minus. In this one, it says 95% confidence. So what's our Z-score? Nope. The Z, you remember there's 3 of them. There's a 90% one, there's a 95, and there's a 99. What's the one for 95? What's the Z-score for 95? 1.96. It's right there at 2. Remember, 90% is, you need to remember those. 90% is 1.645. 95% is 1.96. 99% is 2.576. So they go up. As you be more confident, your Z-score or your standard deviations get higher. Okay? Times the square root of, let's look, the first proportion is 0.16. 1 minus 0.16 would be 0.84 over 50. Plus the second one is 0.20. 1 minus 0.20 would be 0.80 over 60. Okay? So I'm just showing you how they get the interval, which is good to know because you may end up having to it's going to ask you for the margin of error and things like that in just a little bit. So 0.16 minus 0.20 is negative 0.04. And you can see how they get that. That's just a basic subtraction, right? P1 minus P2 gives you negative 0.04 plus or minus 1.96. Now this is the this would be the hardest part to get, is all of that square root. So if I was doing, again, if I'm doing that whole square root, I would take it in my calculator and do just a little bit at a time. Or again, if you want to go into Desmos, you could and go 0.16, 0.84 over 50 plus. But I would be very careful as I'm typing in the calculator that I am not messing up my parentheses. So everybody see, there it is. There is the 0.16 times 0.84 over 50 plus 0.20 times 0.80 over 60. So that's I hate to round, I don't want to round too much in here, okay? So I'm going to go 4. I'm going to say 0.0732. All right? Again, that's coming straight from the formula sheet. And there's the formula sheet with that formula right there at the top. Okay. All right, so we can now go to on Desmos, where I had it. You can take 1.96 and multiply that by 0.0732. We get 0.1434. That's everything on the right. What is that 0.1434 called? Anybody know? The 0.1434, that's our answer. That's what we got all on the right. What is that called? It's what we're going to add to our statistic and subtract from our statistic. It's everything to the right of the plus or minus. What do we call it? It's the margin of error. It's how much you add to your estimate and subtract from your estimate, right? So your estimate, you have an estimate, but you have to have a margin of error, how far you're off one way or the other. Okay. So a couple vocabulary things. This is called your estimate, your point estimate. It's your estimate of what it is. And you get that from just looking at the difference between the two. But then this is called your critical value. Your critical value is the z-score. That depends on how confident you want to be. 90%, 95%, 99%. Okay? This is called your standard error. The critical value and the standard error together create what's called the margin of error. And the margin of error is how much you add or subtract to your estimate. Okay? So we're doing basically what the calculator would be doing. Is 1.645. So we're going to say negative 0.04 minus, and we get our lowest, and we're going to say negative 0.04 plus, and we get our highest. Okay. So our interval would go from negative 0.1834 to positive 0.1034. So we found our interval.
Does it have to be in that order?
Yes, it's got to go. It's got to go from least to greatest. Yeah, an interval has to have. You have to put the lower in the first and the upper in the second. Yes. So that is important. That's a good question. Okay. So now we got to go to stat. I'm just going to check this because typically we may not have to write out all the work, right? Unless we were looking for something specific. On these two problems, we'll be looking for something specific. That's why I showed you all the steps. But on the calculator, hopefully we can get the interval. So in the calculator, we can put 8 and 50, and then we can put 12 and 60, and we have 95%, and we calculate. And we get from negative 0.1834 to positive 0.1034. That's very satisfying when you see that, because you know you did it all correct. Okay, so there is your interval from the calculator. So now you can see exactly what the calculator did to get that interval. It makes you appreciate the calculator even more, that they did all that for you. Now, C is our conclusion. Again, a very important part and one that people mess up in the two proportions. So a lot of times people mess this up because they are not sure what it means. What does this actually mean? Okay, so we are 95% confident. And remember, she talked about that in the video. 95% confident means that 95% of the time we get a result in that interval. So that means sometimes we may not get a result in that interval. But we're 95% confident that the true difference in proportions between the assembly line and its competitor is between negative 0.1834 and 0.1034. Okay? So then we say because 0 is included in the interval, because remember, that's what we look for, is 0 in the interval or not. Because 0 is included in the interval, we cannot say there is a difference. So we're 95% confident that the true difference in proportions between the assembly line and its competitor is between negative 0.1834 and positive 0.1034. Because 0 is included in the interval, we cannot say that there's a difference. So remember, if you get a negative, like we did at the beginning of the interval, if you get a negative, that means your second proportion was bigger, right? If you get a positive, that means your first proportion was bigger. So there are some times when the assembly line has a higher number if we're simulating it for the whole population, and there's sometimes that the competitor has a higher, and that's because their proportions are very close together, right? That's only 4% off, and their samples aren't really large. They're only 50 and 60. So if you get proportions that are farther away and have samples that are a lot bigger, you're more likely to get a result that doesn't contain 0. But if you have proportions that are close together and you have samples that are fairly small, then a lot of times it's going to contain 0 because it's hard to prove that there's a difference. So if you think about it, if it doesn't contain 0, that kind of proves that there's a difference, or it gives you evidence to suggest there's a difference. So in order to make a difference between two things, you want their proportions to be far away from each other. That's the first hint that there might be a difference. And you want to have sampled a high number of people. So those were the couple things here. Now, things that it asks as you go through on here, so just so we can see. B says, what if we decrease the confidence level to 90%? Okay, so if we decrease the confidence level to 90%, the critical value would now be 1.645. That would be the z-score, okay, in B. It would be 1.645, right? The margin of error would now just be 1.645 times 0.0732. So you have to figure out what that is. It would be smaller. 1.645 times 0.0732. That would be your new margin of error, which is what? What'd you get, Giselle?
0.1204.
Okay, so 0.1204. So smaller than what it was before. So if you lower your confidence level, your margin of error goes down. Okay, but you're also not as confident. And then what would the new confidence interval be if you did 90%? Well, you can go to your calculator and do 90% instead of 95. So you go to stat, you go over to test, you go down to 2 proportion Z interval, and it should have your work from earlier, right? It should still have those numbers in there from earlier. The only thing you're going to change is the confidence level. You're going to change it to 0.90. So everything's still there. We just change our confidence level to 90%. And we get an interval from negative 0.1604 to positive 0.08036. That's our new interval. Our new interval if we did 90%. So they're just having you kind of just play around with the problem and see the difference. So we have a new interval there. Okay, let's look at part C. If the sample size were doubled in each and the proportions were the same, and we did a 95% confidence interval, what would happen? Okay, so if we did a 95% confidence interval, the critical value would still be 1.96. It would be the same because it's 95%, right? But what would happen to the margin of error? So what we need to figure out on what would happen to the margin of error is, let's say all the proportions stayed the same, right? But now our samples were doubled. So instead of 50, there was 100 here. And instead of 60, there was 120. So as we look at that, I still had Desmos pulled up from earlier. I can go back. I can't go back. How sad. All right, so I do a square root of 0.16, 0.84 over 100 this time, and 0.20, 0.80 over 120. So now this is 0.0517, and I'm multiplying it by 1.96. So that is my margin of error, 0.1013. What they're wanting you to see is that your margin of error has decreased, right? It went from 0.1434 to now 0.1013. So you got a smaller margin of error, which means you get more accurate results. And the way you did that was you doubled your sample size. That was a way to get a smaller margin of error. Another way to get a smaller margin of error was to do what? Was to decrease the confidence level. That's what we did at B. Now we made our sample size smaller. So if our margin of error is that much, it asks for what's the new confidence interval. Well, again, if you want to, we can go to our calculator and get the new confidence interval. We just have to change it to 100 and 120. So again, now if it's the same proportion, then it wouldn't be 8 out of 100, right? It would be 16 out of 100, and it would be 24 out of 120. Everybody see why I doubled that? And the confidence level would be 0.95. So now our interval is negative 0.1414 to positive 0.0614. Again, it still goes from a negative to a positive, but look at how much smaller it is. We've cut off some of that. So we've made it a more accurate interval. And the way we did that was by increasing our sample size. So what they wanted you to learn from this, from B and C, was that there are 2 ways to make your margin of error more accurate and smaller. The 2 ways are to decrease your confidence level. That means you're not as confident in it. And to increase your sample size. Okay. The goal is to have a big sample size and high confidence, but that's very tough because that takes a lot of work, right? That's why when they're doing trials for new experiments and things like that, it takes a long time for things to happen because that's what they're trying to do, is increase the confidence level with the sample size and all that good stuff. So that is the first question on there, completely worked out. I know it's a lot, but we've learned a lot, and you should be able to carry that forward. So the next question is where I'm going to leave you with, and that's question number 2. You're kind of doing the same thing. You have a nationwide poll of teenagers and adults. You're going to create a confidence interval for those teenagers and adults, the difference between how many have a TV in their room. And then it's going to ask you a couple questions about increasing the confidence level and what would that do if you increase the confidence level? What would that do to the things? And then in number 3, ask you about, it already gives you an interval and just ask you a couple questions about that interval that it gives you. Now, remember in number 3, if it gives you an interval, the sample proportion is right in the middle of that interval. So if you get an interval, the sample or the statistic, your estimate should be right in the middle of that interval. So you could figure out by adding those together and dividing by 2, what's the middle of that interval. And your margin of error, you could then subtract the top from that middle, or you could subtract the bottom from that middle, and you could figure out how much is your margin of error. So that's a hint there for question number 3 when you get to it. All right, so that's what we want to work on in the last part of the class.